we know that somewhere along this interval, the instantaneous slope will equal the average slope. So I found my average slope as being 1 by just doing that difference quotient thing. And then I set that equal to the derivative. And then I did a little bit of equation solving and found out that C, or if you wrote X is fine. X equals 1/2 was the actual X value where that happened. Number 2 is a Riemann sum. Very similar to the ones that we've been doing for the past couple of days. You guys have any questions? Would you like to see something done with 1 or 2? Can I explain what? 2? Yeah. Okay, so 2. Again, I want to be super transparent with you. When I see number 2 and I see the first 4 or 5 words, write a Riemann sum expression, honestly, before I even put an ounce of thinking into this, I write this. Limit as n goes towards infinity of sigma from I equals 1 to n, because I know that all Riemann sum expressions will have that. So I'm not going to overcomplicate this. I'm going to say, I know I got to start there. And then I know that I'm using rectangles. That's what I'm going to be adding up with my sigma. So I'll just put base times height. Now I might not actually write this if I'm doing this on paper because then I got to erase stuff, but I have that luxury here. So far so good? Base. I'm going to draw you a little picture here. Do you see the limits of integration go from 3 to 8? That means that the interval that I am trying to work with here goes from 3 to 8. And, I don't know exactly what this function looks like. I know probably it's increasing. I don't know. We'll just say it looks something like that. So, to me, once you write the limit of the sigma, the base is the next easiest thing to write. So the base is going to be based on the interval width and how many little rectangles we need. So here are a couple of rectangles, and I'll just put ... and that I'm going to fill that with as many rectangles as I want. So the full interval width is 5, right? From 3 to 8 is 5. And I want to be able to use n rectangles. So if the full interval width is 5 and I divide it up into n little parts, how wide is each part? So if the full interval width is 5, right? So from here to here is 5 wide. And I want to split it up. Let's do the number thing. If I wanted to split that up into 5 equal subintervals, how wide would each one of them be? How'd you get that? Five divided by 5, right? So if you have interval width of 5 and you want to split it up into n parts, 5 over n. Does that make sense? Okay. Hey guys, make sure you're solid with this. This will be on your quiz 14 tomorrow. So the base length is 5 over n. The height, could you guys quiet down just a little bit? I feel like I need to stand right by Ty so that she can hear me. And even then, she might be struggling because you're being loud. Height is a little tougher. But let's remember that the height of each rectangle is based on the y value of the curve at the points that we care about. So y value of the curve. So if I wanted to, I could just write y there. But that's not really wrong, but it's not really the full explanation. So instead of y, I'm going to recall that y equals something. Y would equal my integrand. So I'm going to put there input to the 4th minus 1. Y equals x to the 4th minus 1. And so I say input to the 4th because writing the input in there is going to be our last challenge.
And so if it was like x to the 6th, you put like parentheses in
Input to the 6th.
Okay.
Exactly. And that'll be, of course, just customized based on whatever the integrand is. Yeah. Okay, so the last piece of the puzzle is the input. The input, would you agree that the input could be any number between 3 and 8? Mm-hmm. How many numbers are between 3 and 8? A lot. Infinitely many, right? So we have to have a way to generalize this. So the way that I tend to do this is I'm going to say what's the lowest possible input on my interval, and that would be 3. So 3, and then I'm going to put plus, because I'm going to go from 3 to something a little bigger than 3, a little bit bigger than that, and all the way up to 8. So I'm going to go 3 plus. Every time that I move from one rectangle to the next, how far will I move? 1 whole rectangle width, right? 5 over n. So this, I'm going to put 5 over n, and then I have to put times I. The I has to be there because that I need to go from my first to my second to my third to my fourth to my fifth. And from the sigma, the I is going 1, 2, 3, 4, 5. And so if I go times I, that allows me to get to all the rectangles that I need to get to. And I'm done. Okay, let's take a look at number 3. Number 3 is right here. There it is, lovely implicit differentiation question. There's a product rule in there.
Okay, wait, is negative 5 minus 1 the same thing as 5 fourths plus 5?
Say again?
Maybe not. I just did it differently.
You lost your 1, that's the problem. So when you factored out your dy dx, like there's 2 terms here. Term number 1, term number 2. It should be 1 minus that. When you factor out the whole term. See, like on my screen, I did things backwards from you, but we should still get the same answer. Do you see up there I've highlighted it? Do you see my minus 1? You didn't have that anywhere? I think that's what's missing. Thoughts on 3? Or questions? Or I showed pretty good steps. I do tend to go kind of fast through those, but I think steps are fairly well done. We solid? Good? Okay, cool. Do we go to 220? Yeah, 220?
Yes.
220. Okay, cool. I want to do, I'm taking a little bit of a risk here. I want to do this. I want to go just a smidge backwards in time. You remember how we didn't quite finish stuff yesterday?
Yeah.
How I told you some answers to these, and I don't know if you guys had the wherewithal to actually try them, or if you just were like out of sight, out of mind. But why don't you take a couple of minutes, and by that I mean a couple of minutes, so let's transition quickly and see if you can do 6 and 7. I did give you the answers, so there shouldn't be like a big mystery as to whether you got it right or wrong. Please try 6 and 7. Let's make this a quick process, as quick as possible. We can get on what we need to get on to today. So, the first thing I would do is I get 2. Why are you squeeze that stuff? That's 2. It's a 10.
So we don't have negative 2 to 9, but we have negative 2 to 5 and then 5 to negative 3.
The other line, see how the limits? See how the limits actually higher Yes. You guys can see that.
Oh, it can't be that. So you can at least add 2
I don't have an integral of negative y, so those two numbers
Minus 10.
4 times 3.
Just a reminder, there's the answers. Okay, for wherever you've gotten to, do you have some questions? You want to see one of these done? Using those properties, okay, where are we at?
Ready?
Okay. Question?
I'm just wondering how much work you're doing the show.
So I would say 99% of the time these are multiple choice assessments. So whatever you need to. Yeah, so this would be one of those cases where in a question like this, probably you never have to do it. But using that skill, like just need to do actually some of the stuff we're about to do today. So it is kind of a double-sided coin, but like if it was this sort of question, I'd rather use different side of the same coin. One of them has heads, the other has tails. So if I show you the heads and I show you, like if you were 2 years old, I show you the heads, I show you the tails, and you say, which is a different coin?
Yes.
No, it's the same coin, just the same.
Yes. I wish I had hair long enough to hide behind you.
All right. So, hey, let me remind you of what we did yesterday, and then we're going to, so don't turn back. Let me just remind you. Do you all remember, do you guys remember this right here? What was our main method for evaluating those 4 definite integrals? One word answer. Area. We used area. And that worked out super nice. Please listen, this is such a good transition. So, hey, Allie, I don't want you to go to this picture. I just want to remind you of where we went. This worked out super duper nice because this was an awesome piecewise linear graph, right? So finding the area of a triangle several times was very easy. The question has to come up though, what if we're doing some definite integral in the real world and the graph isn't just a bunch of line segments? What if it's curvy and has all kinds of twists and turns? What do you do then? Well, we don't cry in the corner and run away. No. We do what we're about to do today, and that is
Bad idea.
the fundamental theorem of calculus. Yes. Okay.
Are you going to show us how to do those last two?
Am I going to show you what?
How to do those last two?
Well, I asked if anybody wanted to see it, and nobody said a word.
All right, I thought you were showing them.
So I'm not going to do it now. Hey guys, hey, this is what I'm talking about with transition. Gentlemen, when we can't finish at the end, this is why. I should not have to work that hard to get your attention, should I? All right, so fundamental theorem of calculus, there's all kinds of stupid puns we could say here, like you can't say fundamental without saying fun. Courtesy laughs, there you go. But in all seriousness, fundamental, doesn't that mean like foundational? Like this is foundational to what we're doing, right? We can't get away from this. It's important, right? So a fundamental theorem of calculus is something we're going to definitely be pouring a lot of energy into. Now, your book, and I kind of follow with this, your book does split this fundamental theorem of calculus up into 2 parts. So this is fundamental theorem of calculus part 1, an acronym FTC1. It's usually how I refer to it, fundamental theorem of calculus part 1. That's what we're going to be studying today. And tomorrow, not tomorrow. Yeah, tomorrow? Yeah, we'll do fundamental theorem of calculus part 2. Split up into 2 parts. Some books don't do that. Ours does. So if you look very carefully at this fundamental theorem of calculus part 1, you probably can notice a few things. For instance, do you notice that the integrand is f prime, and then on the right side it's no longer prime, it's just f? Why would that be? Yes. Well, an integral. No. What does the tall skinny s mean?
It's an antiderivative.
Antiderivative, indefinite integral, right. So what's the antiderivative of a derivative?
The derivative. No,
The original function, right? Don't they cancel out? They cancel out. So the antiderivative of a derivative, they just cancel out. And so maybe that makes sense then that the antiderivative of f prime would just be f of x, right? Okay. And then notice how this b has kind of dropped in as the input, and then this a has dropped in as the other input, and there's subtraction. Okay? So then when you look at these ideas down below to use FTC1, step 1 is to find the antiderivative. Thankfully, that's something we've put a lot of energy and effort into, and we might not be perfect at it yet because we still have some quiz retries to do, but you should have a decent sense. You should have a decent sense of what to do, right? And you know what? If you don't, guess what you're going to get some extra practice on? Antiderivatives. You're going to get plenty more practice even today on this. Once you have found the antiderivative, you're going to plug in the upper limit and the lower limit, subtract then in that order. Okay? Plug in upper limit minus plug in at lower limit. Okay? So, as I walked around and I was watching you guys doing your warm-up, I actually saw some of you guys moving on to this, and I'm guessing, maybe if you're in Physics C, you have done some of these before. Maybe in some other setting you've done some of these. I am going to show you, for a couple of these, I'm going to show you 2 different ways. Don't fall into this trap of thinking to yourself, oh, I already know how to do this, so I'm going to do it my way, and I'm going to ignore the other way. You really have to be good at both ways. Okay? You can use one method the majority of the time, but there are going to be times when you have to be able to use the other methods. Okay? So here we go. I'll show you way number 1. I'll do something like that. So way number 1 would be this right here. I'm going to rewrite a little bit just so I have room. But I would say the first method would be maybe using the Timmy messed up the chain rule pattern. And the reason why I'd even consider using that is because I clearly have a composite function. There's even some elements of a product in there. So if I was going to do the whole Timmy messed up the chain rule pattern to find my antiderivative, I'd need to look at the inside and ask myself, is the derivative of the inside equivalent to the other factor? And the answer is? No. But close. He's off by a factor of? 2. So I could go in there and say, all right, times 2 times 1/2. I still have my integral from 1 to 2. Remember, we've named that from bottom to top. The 1/2 does not go anywhere. And let's practice our antiderivative. What happens to the 2x? It goes back in the box, right? And then the antiderivative of something to the 4th, what do? There we go. It's a power rule. Yeah. So we add 1, so we get x squared minus 3 to the 5th. And then we would divide by 5, so that would really just be times 1/5. Now here's where things are going to be a little bit different. Please listen carefully. I don't have to write a plus c in this case.
Oh, yeah.
But to prove that I don't have to, I'm going to write it, and then you can see why I really don't need to write it. Does that make sense? So I'm going to put plus c. When I'm doing a definite integral, I really don't have to do that, but you'll see what happens in a second. Here's some new notation. This might be new for just about everybody. I'm going to put that whole antiderivative in parentheses. I'm going to write a vertical line. You've seen this before. And then I'll write the 1 and the 2. What that means is the antiderivative evaluated from 1 to 2. So that vertical line means evaluated from. We've actually used it before where we said evaluated at, and we just had a single value. Now it's two values, so it's evaluated from 1 to 2. Brendan?
We just don't need to write the antiderivative or the integral symbol.
In fact, yeah, you shouldn't because you did do the antiderivative. We already did it, so we shouldn't write it again. Yep. Okay, so here's what happens next. I found my antiderivative. Now I'm going to plug in the top value. I'm going to plug in the bottom value, subtract. So here's what that looks like. 1/2 times 1/5 is 1/10. So it'd be 1/10 times 2 squared minus 3 to the 5th plus c minus, parentheses, 1/10 times 1 squared minus 3 to the 5th plus c, like so. So I plugged in the 2, I plugged in the 1, I'm subtracting. Do y'all see what happens with the c's? You're going to add out. What's c minus itself is 0, isn't it? So because of that, you will never see me write plus c again on a definite integral for the rest of the year unless I have to like reprove this to you. But when you're doing a definite integral with the two limits like we're doing right now, you do not have to write the plus c at all because it's just going to add out 100% of the time. So we don't have to worry about it. Okay. So what follows here is just some arithmetic. So 2 squared is 4. 4 minus 3 is 1. 1 to the 5th is 1 times 1/10 is 1/10. And then the other one, 1 squared is 1. Minus 3 is negative 2. To the 5th is negative 32. So this would be minus negative 32 over 10. So I'm coming up with a final answer of positive 33 over 10, or 3.3, right? Why what?
Why
Okay.
did you do the second part, the 1/10, put minus, and then
When
I
you-
get it up to that.
When you say the second part, are you talking about this?
Yeah.
Okay,
Well, that whole equation.
this?
Yeah.
Let's
Why
go-
do you do that?
Let's go back to the fundamental theorem. Fundamental theorem says if you're doing the definite integral from a to b of f prime of x dx, that equals f of b minus f of a. This is this.
Oh, so for x you just plugged in.
I
B.
plugged in the upper limit. I plugged in the lower limit. And I subtracted the two of them.
Oh, gotcha. Thank you.
Okay. Yep. Any other questions on that one? Okay. So guys, I'm going to show you now the alternative. Did I miss any questions? Okay, I'm going to show you the alternative to this. This is not an alternative as in, I like that way. I'll just do my way. You need to know how to do both ways. So I'm going to draw a line here. I'll use a different color. So this other method has a couple of names. They all mean the same thing. This other method is called substitution. Some people refer to it as substitution. Some people refer to it as U substitution. Other will refer to it as change of variable. And if you think about it, isn't that what substitution is? Like you're changing the variable from one to another. So I tell you those things not to confuse you, but just let you know they're all synonymous, right? They all mean the same thing. You might read them in different... If you look something up on the internet, you might see any one of those. So whatever. Okay, so when we're doing substitution, thankfully this is something we've already done. We're going to always set up our u to be something in particular. We always set the u to be what part of the expression? The inside. That's right. So what's the inside on this one? That's right. And then when we're doing substitution, don't we always need like a du and a dx kind of a substitution? So we always write du equals 2x dx. Okay, so once I've gotten these two things in place, I can start substituting. So I'm going to write integral. I'm going to plug my iPad in because I'm a little bit low on battery, which means I'm going to be tied back here for a few minutes. So I apologize. Oops. For standing back here. Anyway, So I start my substitution. Y'all okay if I wrote x times u to the fourth dx? Does that make sense? Okay, so then I've got to handle the x and the dx. Do you guys see anything I could replace either the x or the dx or both? Say again? Yeah, can't I use this and just say, yeah, du over 2x equals dx? This is one way to do it. There are other ways, but this way will work fine.
Doesn't it make it harder?
Well, let's run through it real quick. So here's what it would look like. Couldn't I replace the dx with du over 2x? If I did that, what would happen with the x's? So the x would cancel with the x, giving me 1/2 integral of u to the fourth du. Can I show you an alternative way? Check this out. What if I, instead of doing that, what if I said du over 2 equals x dx? So Grant divided by 2x on both sides. What if I just divided by 2? Check this out. X dx. X dx. Couldn't I just replace the x times the dx just in one shot? Du over 2? So I just want you to be flexible in your thinking. Grant's way works fine. My way works fine. We could even think about it a slightly different way as well. Remember, substitution is based on the idea, if this thing here equals that thing there, I can do this. And that's all I'm doing. I'm saying x times dx is the same thing as du over 2. So I can just do a little switcheroo, aka substitution. So here we go. Either way, no matter how you slice this, you're going to get antiderivative of u to the fourth times du. And then maybe you guys remember, I'm never going to write the over 2 in the integrand. I'm always going to pull that out as a 1/2. Have you guys noticed that up to this point, I have not written those limits of integration? It was a 1 and a 2, and I've on purpose left them blank. I want to explain why. When you think about areas and such, the original 1 and 2 isn't the 1 where we start accumulating area, and isn't the 2 where we stop. So for that reason, I would say that the original 1 and 2 are x values, and so I'm converting everything over to u's. So I need to convert the 1 and the 2 over to u's also. Otherwise, I'm going to be shifted way off on my graph. So if the original low limit was 1, here's my original low limit. I have one thing and one thing only that relates u and x. What relates u with x? Yeah, the top equation, right? U equals x squared minus 3. So you tell me, if x is 1, u is -2. So my new low limit is going to be -2.
I'm sorry, where'd you come out of the 2?
So, okay, so my old low limit, just watch the screen. My old low limit was 1, correct? The only thing that I have that relates the u with the x is right there. So what I said earlier, I think I would say it the same way. If x is 1, wouldn't I plug a 1 in for x? What's 1 squared? 1 minus 3 is -2. -2. Does that make sense? So if x is 1, u is -2, but the old high limit was 2. So if x is 2, u is 1. So watch this. This is going to come together really, really nicely. At this point, these look very different, don't they? Like I said, it's about to come together really nicely. The 1/2 doesn't go anywhere. What's the antiderivative of u to the fourth? That's right, 1/5 times u to the fifth, evaluated from -2 to 1. So this would be 1/10 u to the fifth, evaluated from -2 to 1. And already, can you see how the 1/10 that we were hoping was going to show up is there now? Yeah. Okay, but the 1 and the 32, the negative 32, those don't seem to be there at all. Let me keep going. So this would be 1/10. Now I'm going to plug in. So I'm going to plug in the top limit. Wouldn't that be 1/10 times 1 to the 5th? Minus 1/10 times negative 2 to the 5th. Should be coming together now, right? So 1 to the 5th is 1 times 1/10 is 1/10 minus 1/10. What is negative 2 to the 5th? 32. Negative 32, right? So times negative 32. So I get 1/10 plus 32 tenths. And check it out. It's all the same. So which one is better for you? That's going to be kind of a personal choice. The one that you have to be good at is really the blue one. The blue one will be assessed in ways in which you don't even have to go through all, don't stress. You don't have to even go all the way through with what I just did there, but you have to know how to substitute, and you have to be able to deal with those limits of integration, like the switching of them from x's to u's. If you wanted to use the gray and red one a lot, the gray and red one is going to work a lot.
So we don't have to use it, right? I mean,
You really don't have to use the gray and red one at all. But I like it because it's fast. To me, it's faster. Blake, go.
Last rule we got the negative 2.
Sorry, say again?
On the bottom, like where you start, counting area, for the last rule we got negative 2.
The whole thing's shifted
Why did it shift though?
because I switched from x's to u's.
And that shifts it where?
It doesn't. It moves. It's like it's hard to say the shifting because the inside was x squared minus 3, right?
Now you don't have it.
So graphically, it's the same graph if you're going to graph y in terms of x. But here's the point, though. Like think of it like this: if these are x's right here, like if these are x's and these are u's, how in the world can you justify plugging an x in for a u? You can't. But if I said u equals negative 2 and u equals 1, and I'm going to plug those in for u's, well, that actually makes sense. So if I'm converting over to u's for my variable, I have to have my limits as u's too to be able to plug in. They need to match.
I just don't get what the word negative.
You don't get the word negative?
No, where negative 2 comes in.
You're not sure where it came from?
Yeah.
Oh, okay. So the only thing that I have that relates u's and x's, I'm going to circle it a bunch, is right there. So if the old x was 1, then u would equal 1 squared minus 3. 1 minus 3 is negative 2. Is that it? Okay, gotcha. Okay. Hey, let's check out number 2 real quick. Interesting. So number 2, let's do this one together. What do you see, what do your eyes tell you as far as something we could do to make this simpler? Got to get the 3 out. I agree. So that'd be my first step. And you're left with secant squared of x in there. Okay. So fundamental theorem of calculus part 1, what you do is you find the antiderivative. And this is one where it's really handy if you can recognize that secant squared is just the derivative of? Hey, that's nice. So the antiderivative of secant squared would get to tangent. Yes, very good. So it'd be 3 tangent of x evaluated from 0 to pi over 4. Again, I'm trying to use that same notation. That vertical line means from 0, evaluated from 0 to pi over 4. And then the finish of this is going to involve a little bit of that trig unit circle stuff that you did a lot of in the past. This would be 3 tangent of pi over 4 minus 3 tangent of 0. What's tangent of pi over 4?
1.
It's 1, yep. So this would be 3 times 1 minus 3 times. Tangent of 0 is 0. So my final answer here would just be 3. It's a little simpler. I mean, I guess people could argue that it's not because it's secant squared, but whatever. You get the idea. How you guys doing? Okay. So let's do I do want to get to 5 for sure. Let's look at 3, and let's do this one together. Let's see if we can get a little back and forth going here. And since it's probably a little less familiar, let's do number 3. We'll at least start 5. But let's get 3 in here, and we'll at least kind of set 5 up, and we'll get to 5 tomorrow probably for sure. So let's do substitution on 3. I want to get a little bit of feedback from you guys. If I'm going to do substitution, I've got to set up my u. What do you think the u should be?
X cubed minus 7.
That's right. X cubed minus 7. We always need a du. What would the du equal? Don't lose the dx, please. That dx has to be there for this to make any sense. So du equals 3x squared dx. So I'm going to start substituting. I'm not going to write my limits of integration in there anywhere. Not yet. So I can replace the x cubed minus 7 with u. So I would say u to the 1/2. But if I'm honest about this, I still have an x squared times dx. Does anybody see anything we could substitute in for the x squared dx? Say again?
Dx equals du over 3x squared.
I kind of favor this, as I said before. If I divide it by 3, wouldn't du over 3 equal all the stuff that we need to go away?
Yeah.
So I can replace that with u to the 1/2 times du. There's my over 3. So this would be a good chance to revisit what we just did. Again, notice that I've not written the limits of integration. I didn't write the from 2 to 3 yet, and that's because I could see into the future, and I knew that I was going to convert them from x's to u's. What am I going to use to convert them from x's to u's? I just highlighted it in red, right? Okay. So if the low limit used to be a 2, I would think to my head u equals 2 cubed minus 7, which is 8 minus 7, which is 1. Or I can write u equals 3 cubed minus 7, which is 27 minus 7. My new high limit is 20. Here's what I want you guys to think about. Now that I've converted all the way over to u's, it's almost like I just married the u's. I'm bonded with the u's. I'm stuck with them, right? No matter what, the u's are, that's what I'm doing. Okay, I'm not going to go back to the x's. So I'm just going to find my antiderivative, plug, subtract, done. Here's how this would look. 1/3 times 2/3 u to the 3/2. Just a regular old antiderivative evaluated from 1 to 20. This would then equal 2/9 times, I don't have a clue what that is, I'm just going to write it like that, minus 2/9 times 1 to the 3/2. So I can clean this up a little bit. I could just write it as 2/9 times 20 to the 3/2 minus 2/9. But absent a calculator, that's about as far as I care to go. The truth is, if I had a calculator and I was doing this, I would do something entirely different, which you guys will learn about soon. Which is actually Math 9. Okay. Hey, I want to just give you a brief preview of what we would do with 5, and we should have time tomorrow to revisit this. So, what was that, Mitch? So Mitch looked ahead. Anybody freaked out? Please don't pack up yet. I got 30 seconds. I'll use all 30 of them. Anybody freak out a little bit when you see this? It says find the definite integral from 0 to 2. Did you notice that the 1/2, like where the domain switches, is in between the 0 and the 2? So here's what you would do to make this a little less scary looking. You would take this and you would split it up. Integral from 0 to 1/2 of g of x dx plus integral from 1/2 to 2 of g of x dx. And then you just treat it like two separate integrals, which stuff we've already been doing for this class today. So that makes it a lot easier when you split it up based on the way the domain works. Hey, don't forget tomorrow is quiz 14, and then we'll continue to practice Fenel theorem after that. So have a great rest of your day.
I really need to make up my quizzes.
That's why if I failed my first test, I